All right, welcome to your last topic for the semester. So we are going to look at probability in this last section for week 8. And this is section 12.1 from your textbook. And it is going to be just a very, very introduction to probability and statistics. So, I mean, really, we're just going to kind of do some basic introduction. We're not going to dive very deep into it, but we will lay the groundwork should you ever decide to further your studies in probability. So first, the first thing that is necessary when you are calculating probability or when you are looking at the number is actually the first thing when you want to talk about probability is calculating the number of outcomes that are possible. So that's really all this lesson is going to deal with is how do we determine how many outcomes are possible, whatever the scenario is, right? We're not actually going to calculate the probability of an event happening or look at the statistics of it. We are just going to talk about how could we get the total pool of outcomes, because that's the basis for doing any of those other things. So the first and simplest way is just to make a list, right? Like say I'm flipping a coin. Well, if I'm flipping a coin once, it's pretty easy. My list is heads or tails. But if I'm flipping a coin twice, right, I could have heads, heads. I could have heads, tails. I could have heads, tails, or I could have tails, heads. So that would be making a list of all the possible outcomes. Now you can see that the more times you do the experiment, that's what we would call flipping the coin, the experiment. Whatever the event is, that's the experiment. So you can see that the more events that you have going on, the more complicated and long the list gets. For example, rolling to die, they have 6 sides. So not just 2 outcomes, heads or tails, but 1 through 6. And then every time you roll the die, you get 6 more. So the next way that you can list out all the outcomes to get a total count would be to make a table. And so your book gives you an example of that with the die, the rolling the dice, just like I said. You could do 1 through 6 across the top, 1 through 6 across the bottom, and then just fill in your numbers, and you will get a grid of all the possible outcomes from rolling 2 dice. Obviously, if you had 3 dice, that gets more complicated. So that leads us to the third method you're going to look at, and that's tree diagrams. So tree diagrams look a little bit like prime factorization, but the way that you accomplish it obviously is not the same. So you would start with, okay, the first event, if we're going back to flipping a coin, right, I have heads and I have tails. Well, from that heads, if I flipped again, I could get heads or I could get tails. So you just do the outcomes as branches. And then in the end, the very last row of or column of things is the total number of outcomes that are possible. So again, I don't think these ideas are very complicated, and your book does a great job of actually taking some specific examples and writing out the steps. So you're going to practice making lists, making tables, making tree diagrams. I think that you'll quickly realize that for a complicated experiment or for something with a lot of outcomes, all of those methods are very tedious. It could take a very long time to draw tree diagrams if you have multiple, the higher the outcomes get, right? So that kind of was the driving force to come up with some mathematical equations, some mathematical formulas that would allow us to calculate these outcomes without having to draw out all the lists and possibilities. So the first one that we can come across is the counting principle. The counting principle was developed and has been proven to be true to help calculate exactly what we've been saying, the total number of outcomes. Now, if you look in your math textbook, you're going to see a box that says the counting principle, and it has it written out all in, beautiful math language with all its symbols and its formulas, and it looks very complicated, but it is actually a very simple idea. The counting principle simply says that if you are doing a certain number of events, right, like flipping a coin twice or rolling 2 die, right, so each one of those have 2 events. then the total possible outcomes is the number of outcomes for each event multiplied together. So, for example, if you flip a coin once, there are two choices, heads or tails. The second time you flip a coin, there are two choices. So there's 2 and there's 2. The counting principle says if I multiply 2 times 2, I get 4. That's all the possible outcomes added together. The same for the dice. If you look at the chart in your book, the table, where they've written out all the possibilities, and you count up the squares, you will get 36. The reason that you get 36 is because when I roll one dice, one die, there are 6 options, right? 1 through 6. When I roll the second die, there are 6 options, 1 through 6. The counting principle says I can multiply 6 times 6. I get 36. 36 are all the possible outcomes. And you have listed those out to see that. Another application would be, say that you're at a race. There are 7 participants in the race. You want to know how many different combinations of first, second, and third winners are there, right? So because I'm only looking at first, second, and third, that means that there are 3 events. So for the first place finish, there are 7 competitors. There are 7 choices. But once that person finishes, there are only 6 left for the second spot. So the second event only has 6 choices. Then for the third spot, there are only 5 choices because first and second are out. They can no longer finish third. So to find the total outcomes for first, second, and third place, we would multiply 7 times 6 times 5. You'll see that's a very large number. So if you had to draw a tree for that, it could take a very long time. Fortunately, the counting principle lets us not draw a tree. We can just do simple multiplication. So the race example highlights one thing that really the main thing that you need to be careful of when you're doing these problems. Your book will call it, and it's common language, it's kind of what we use in probability. You can have an event with replacement or without replacement. So in the race example, that was an example of without replacement because once a racer finished first, they were out. They were no longer in the race. We didn't consider them. So they were removed from the second event. For the race to be counted, it really doesn't even make sense to talk about a race with replacement because that would mean once they ran first, they go back into the race and are still part of the field, right? So it doesn't really make sense. Where it might make sense to talk about the total outcomes with replacement is say you're finding a 3-digit code, right? And you want to use the numbers 1 through 9. So you have 9 choices for each spot, and you can repeat numbers, right? So if I put a 2 in the first spot, that doesn't eliminate 2. I can keep 2. It could be 2, 2, 2, right? So for each spot, we're not taking numbers out and removing them. We're keeping them all in. So with replacement would mean that my 3 events would be 9 times 9 times 9. Those are all the 3-digit codes that you could make with 1 through 9. Now, if you wanted to talk about what that would look like without replacement, what you're saying is a digit can only be used once, right? So the first slot, whatever number I use is then removed, can't be reused. So then you would have 9 times 8 times 7. Okay, that's the counting principle. Hopefully you should find that pretty straightforward, and you will be done with this class.